let's go to the next design step of assembly and packaging, and that is thermal design. Thermal design is also called thermal management. And first I would like to introduce what the problem is. So, as we can see here, this is a power device which is a very modern IGBT, and that device has very high currents, as we can see from these many thick copper wires which interconnect that device. When the device is switched on under a large load, we can see there is a hotspot in the middle of that device, and the hotspot reaches a maximum temperature here of 176 degrees centigrade. Ooh, that's hot. And now the question is, can we predict what the temperature will be in the semiconductor or in all of the other parts of the assembly? And that's what we are going to deal with today. But now let's go away from power electronics. Let's go to digital logic components. There is in literature a formula which gives an estimate of the power dissipation in logic devices, like in an ASIC or in a microcontroller. And that says the power is proportional to the number of elements we have in that device. For instance, the several hundred millions of transistors in a processor. It is proportional to the frequency. So the higher the frequency, the more often we turn off a bit and turn it on again. Typically, we charge the bit in a capacitor, and so we have that so-called parasitic capacities. And the larger it is, the more energy is stored. Of course, in a capacitor, the energy is proportional to the square of the voltage which we use to load it up. And there is one more point, which is the circuit activity factor. That means in a 100 million transistor processor, not all of these transistors are turned on simultaneously, but only some. That's depending on the load. Okay, now let's have a look at typical data. For instance, frequency goes up to a gigahertz or so. The voltage was decreased from 5 volts many years ago to 0.5 volts. The parasitic capacitance was decreased by many orders of magnitude, because let's say we went from the 1 micrometer scale of our devices to the 10 nanometer scale, and that means a factor of 100, and 100 to the power of 3 is a million. Yes, so parasitic capacitances were reduced significantly. Frequency was increased also significantly. Maybe a processor had 10,000 of transistors in the year 1980, and now it has 1,000 or 10,000 more, and that alone would mean an increase of the power dissipation by a factor of 10,000. Imagine we had 1 watt at that time, and now we would have 10 kilowatt for a modern processor. At the same time, the frequency was also increased by a factor of also 1,000. 1 megahertz went to 1 gigahertz. So that would mean 1 billion increase of power dissipation. And in that way, we could see that a microcontroller controller built in the technology of the year 1980, it would dissipate tens or hundreds of kilowatt. And that, of course, is not tolerable. So the decrease of the voltage, the decrease of the capacitance, and of course also that circuit activity factor. So modern processors only turn on that part which is really needed for the computation, and so in idle mode some parts of the computer don't use very much power. So in that way we can estimate how much the power dissipation can be, and it also gives us a good guess what the influences on power dissipation in logic circuits are. On the other hand, when we have a continuously operated power MOS, that is something like a very low ohmic resistor that is turned on. And so when it's turned on, we have minimum resistance, on resistance between drain and source of only, let's say, several to tens of milliohms. And in that way, when we multiply that on resistance with the current we want to switch, we get the power dissipation in that power MOS device. So that means the development of such small power devices was characterized by decrease of the RDS on, of the on resistance between drain and source. Now let's go back, have a look at such IGBT transistors, and here we can see in such transistors we also have one gate which you cannot see here, but when the gate is turned on and off, that device is switched, and it is not so easy to predict the power dissipation in an IGBT power module, but we must say IGBTs are made for maybe 0 to 200 amps and typically 0 to 1200 volts. Some go even higher in voltage. And here we can expect a high power dissipation. So the switched power is just these this multiplication. Here in that case it's 0.2 megawatt, and when we take that switched power and we take between maybe modern devices it's rather 1% and 10% of that switched power, then we get the power dissipation. So we can say a typical electro vehicle, for instance, if it's a small one, not a Tesla, and it has only 40 kilowatt, it has a power dissipation between 1 and 2 kilowatt. So that's heat that is lost mainly in the IGBT and heats it up to such temperatures, or even higher when we do not have a proper design. Okay. But there are more effects. The dissipated heat leads to heating, not only of the device, but also of the environment. And if the operating environment of the device is heated, that's an additional temperature increase we can observe. Okay. There are other sources of the operating environment. For instance, that was a Mercedes commercial car. in fact, it was some Unimog. And here my colleagues, they wanted to put a sensor into the gear box. And they made a test drive before they installed such a sensor. They just wanted to see. So in fact, they are close by and near the Rhine, and so there they looked for the temperature. For instance, if they are in lowlands, temperature is somewhat higher. Driving up into the Black Forest, temperature is somewhat cooler, and so you have several degrees of centigrade. That means just the altitude at which you drive is a little different, but of course the environment can be quite different between Death Valley in California and some coldest point in Siberia, for instance. So the temperature differences of the environment can span a range of roughly 100 Kelvin. Okay, now let's have a look at our gear oil. So it goes up, the car is heating up, but also depending on the mode of driving, there is some variance of temperature. And when we look at just test points where we wanted to install electronics, we can say, okay, it's quite variable and temperature goes up to roughly 80 degrees centigrade. So we must take care when we make a design of the environmental temperature. It is important that this temperature comes in addition to the dissipated heat temperature inside the device. Okay, when we know temperature, that is very helpful, because then we can also estimate what the effects, for instance, on mechanical phenomena are. And how could we proceed in such an industrial design process? So first of all, for instance, in the power electronics, we have a CAD draft. When we have a draft and a schematic, we can make a electrical simulation. In the easiest case, we use SPICE or some similar simulator. What we get is the power dissipation in devices and over time. So for instance, that was for an electro vehicle which just started to drive. So the frequency is very low. That's in the IGBT and that's in the diode. And in that way, the power dissipation can be estimated. It's not so easy because power dissipation, again, is dependent on the temperature. But now, let's assume we have a first estimate. The second is not only the power dissipation, but it's also the cooling. And when we want to have high power cooling, then we must estimate how the heat is exchanged with the environment. And for instance, here we have water cooling. And in order to estimate the dissipated heat in a precise way, we can use CFD, which is computational fluid dynamics. In that way, we get data, and if we unite both data and also take together the solid state behavior of that device, we get the thermal management and we get the temperature distribution. For instance, that can be interesting not only for the device, but it also can be interesting, for instance, for the bonding wire, because that could be overheated and it could just flame off, for instance, due to excessive currents and due to excessive temperature. On the basis of that temperature distribution, we can also compute local stresses and strains. This is important because we have seen thermal mechanical stress is really a killer for electronics. And when we know local stresses and strains, then we can also make a lifetime prediction, and we can make a prognosis of the reliability of these devices. So here, to that purpose, you can also go into my lecture in the winter semester, which is called Reliability Engineering, where we have more information on why devices fail and what we can do to model that. Okay. Now, you must imagine the people who design electronics, they typically are not engineers specialized in thermodynamics. They are electrical engineers, and of course they would like to resort to techniques where they are familiar with. And of course the resistance is a very good let's say property where you can have a good imagination as an electrical engineer. And to that purpose, the idea was, normally when we have an electrical resistance, that electrical resistance is the ratio between voltage and current. On the other hand, we can also say, yeah, the behavior between power and temperature increase, in many cases it is linear. More power leads to more temperature increase. Where is the power in the transistor dissipated originally in a PNP transistor, for instance? It's in the PN junction. So here we say where the heat is dissipated is the junction, and where is the heat drained? It is in the ambient. So it's a temperature dependency between the hottest point and the ambient. That's a delta T. And that delta T over the environment, it is proportional to the power. In that way, we can define a thermal resistance, junction ambient, which is just the temperature increase. So that's potential difference here divided by the heat flow per time, and that's just the power. Yeah, power is energy per time. So in that way, we can model it, and when we have a more complex device, we can say that device, for instance, that device is modeled. For instance, when we would have a power device which is mounted on a sink, so here we have the junction. From the junction it goes to the case. That's the sink. And here we have the ambient. And then we can say there are three resistors, which is or three temperature steps. One is from the junction to the case. So here is you could say it's something like a voltage between junction and case. You have it between case and sink. And you have it from the sink to the ambient, to the air, or to the water. And in that way, you could estimate what is the delta T junction case, and what is the delta T case sink, and what is a delta T sink ambient. And so, because temperature is proportional to resistance, resistance is proportional to temperature, you could say the resistance is the resistance junction case plus the resistance case sink plus the resistance sink ambient. And in that way, the temperature increase is the power multiplied with the sum of these individual resistances. Now the trick is, these resistances are not so hard to get. For instance, junction case is often taken from manufacturer's specification of devices, and the junction case to sink and the resistance case to sink and the resistance sink to area can often be taken from the data sheets of manufacturers of heatsink. So in fact, if you want to have such data, you can look on the respective pages on the internet and you find typical data. Now let's have just an example. If we have so small devices, for instance, dual inline package, but also the versions which are SMD versions here, we can say, so typically we have 70 to 110 Kelvin per watt. So that would mean the thermal resistance is quite high. 1 watt of power dissipation would already lead to an increase of temperature of up to 110 degrees centigrade at the hottest point in the device. If we have larger devices like such PLCC, which is SMD devices, the thermal resistance can be significantly lower. On the other hand, bigger devices have bigger chips, and bigger chips dissipate more heat in most cases. Here are other devices which are more, for instance, TQFP. Depending on how they are built up, they can have between 8 and 100 Kelvin per watt. And so here are different examples. If you want to have a device which has a very low thermal resistance, for instance, you could take BGA, which has 352 IOs. And for instance, here we have a thermal resistance of only roughly 3 Kelvin per watt. On the other hand, such a big device can also have a big power dissipation, as we all know from our PC. For instance, imagine it would just have a power dissipation of 30 watt. That would lead in a temperature increase of 90 Kelvin. Again, it's a very high value. Now, people have started relatively early to find out what the influence of materials is on the thermal resistance. So it's better here to write Kelvin per watt. So here we have different materials: plastic, aluminum oxide, aluminum nitride, and aluminum nitride with pin-fin. That's a QFP. The QFP device looks like this, but also, of course, it has on all sides IOs, and that's QFP 160. So that's the QFP we have, and if it has pin fins, it just has such a structure on top, which can increase the surface area, and in that way the heat is dissipated to the air. So the materials were, what we can see here. Plastic, that's typically a molding compound. And when we just have the device with a certain power, okay, we have a temperature increase of 60 degree per watt. So we can see it's relative high temperature increase, and the more we blow air over that device, the more we can say the cooler it will become, and that we can see the thermal resistance will be decreased. If we take aluminum oxide, the thermal resistance generally is lower. Why is it so? The aluminum oxide will distribute the heat better in the device, and so in that way, generally, the area which can be efficiently cooled will be larger. Here we can say the heat conductivity is, let's say, 0.8 watt per meter Kelvin. Here lambda is roughly 20. Here lambda is roughly, let's say, 150. And of course here lambda is also 150, but here area is larger. And in that way, we can decrease the thermal resistance significantly, but in the end, also, how strong we blow, we never get the thermal resistance to 0. What's the reason? Even if the outside thermal resistance, which is the thermal resistance sink to ambient, even if that would be 0, the internal resistance, junction to case and case to sink, would still be there. And in that way, there will be always a residual thermal resistance. Now let's have a look at these mechanisms of heat transfer. So the first is thermal conduction. Here we have Fourier equation that says the power density or the heat flux, that is power per area, is proportional to the thermal conductivity of the medium in which we dissipate the heat and the gradient of temperature. Please note that the thermal conductivity can be temperature dependent, but in our lecture we assume it to be constant over temperature. The second is the convection on a wall. So imagine we have a part which has a temperature T and where we blow with air. And so we have here the wall, which is the surface of our device, and here we have the fluid, which can be air or water or oil. The heat flux or the dissipated power density is proportional to the delta T between the surface and the fluid multiplied with the heat transfer coefficient. The heat transfer coefficient is measured in watt per square meter and Kelvin. So for instance, if we have a heat transfer coefficient of 1 watt per square meter and Kelvin. That means we have an area of 1 square meter. The wall has a temperature of, let's say, 1 degree. The environment has 0 degree, and in that way, on that square meter, we dissipate 1 watt of power. Typical when we have free convection of air, so we do not blow artificially or with a fan. The typical range is 1 to 10 watt per square meter and Kelvin. That depends on many parameters. When we have a fan, then we are in the range of 1 to 100 watt per square meter and Kelvin. So we have forced air. And in many cases, it's advisable to use forced convection of water, and that can be in the range of 600 to 10,000 watt per square meter and Kelvin. Some people doing MEMS coolers, they even claimed 100,000 watt per square meter and Kelvin, but that can be achieved, but that cannot be maintained over longer times. Okay, so that are typical ranges of heat transfer coefficients. Radiation, here we can say the dissipated power per area is proportional to the temperature to the power of 4. And then we have also phase transition. Here we can say the phase transition is, for instance, evaporation of some medium. For instance, imagine you would have your electronics in water and you would just boil the water away. Then you would keep the temperature at 100 degrees centigrade, or you have it in some kind of wax, for instance, and that wax would melt, and then you can keep it at the melting point of that wax. The dissipated power density is some constant, which is more or less the specific heat for the phase transition. So that can be the heat of fusion, that can be the heat of evaporation. And if you take that specific heat and multiply it with the amount of material which is converted per time, and again take that energy per area which you cool, then you get a value for the phase transition. So you can use phase transition, and for instance in a heat pipe it is done in that way. Now let's have a little more look at the details of the individual heat transfer processes. Imagine we have one element of material and that's a block where the heat goes in, and imagine the heat goes out, and over that block, which has a thickness of d or delta x, we have an area, and also that block has a certain heat conductivity which we can see here. And in that case, the thermal resistance of such an individual block under steady state conditions is the thickness of that block divided by the thermal conductivity or heat conductivity and divided by the area which we regard. So important factor is the thermal conductivity. Here are some examples. We have more data in the lecture notes. For instance, metals typically have between, for solders, 30 and 60 or 70 even watt per meter Kelvin. Silver has roughly 400. Copper is almost like silver in the heat conductivity. Aluminum oxide, for instance, can be taken as 20. Aluminum nitride is temperature dependent, so it is somewhere in the range between 110 and 180 degrees. Watt per meter Kelvin in the between 20 and 300. And if you want to go for non-steady state calculations, that would be the case if more heat goes in than can go away. In that way, we would not only have a delta T over D, but then we also would have a delta T over time. That would be transient, that would be steady state, but we will only address steady state heat in this lecture. Okay, so if we have many layers in a sequence, we can say, okay, we make a chain of resistors. Of n resistors, then we can just say the resistance is the addition of all individual resistances. In case we have the resistors in parallel, then we can say, okay, the total resistance is given as the inverse of the total is the sum of the inverse values of the individual resistance. Of course, when we have a more complex circuit, we can again give more and more. So we can assemble it from parallel and serial resistors if it's a complex device. So just to give you an example here, I found in one of the textbooks. That is a device which is made of aluminum oxide. Here we have a flip chip mounted chip. The chip is not only cooled via the balls of the flip chip, it's also cooled with a thermal pad or a grease to the top of that cap. And now the heat goes to the ambient via several ways. Maybe we could discuss about that, if that's really a proper thing, but the idea is you just decompose it into resistances which you can easily estimate. And in that way you could say, okay, you have the resistance cap to air, you have the resistance card to air. Of course, you must make an assumption here about the area. For the cap, it is clear. You have the resistances going from chip via flip chip and pin into the card. You have some resistance in the card, And in that way, you can make a proper model. Of course, you could say, yes, here you have thermal ground, and here you just put your voltage against ground, and in that way you have that thermal network, and by taking the resistances in parallel and in series, you can estimate what the total resistance is. In fact, I must say, such method is quite efficient, especially if you take more resistors. Maybe here we just have 2, 4, 6 resistors, but it's no big work to make more, like 12. And in that case, if you have even a large mistake in the data you assume, for instance, you assume in one value you are wrong by a factor of 2, but that means, or you could be wrong by 50%. Yes, if it's 10 devices, in the total it will only make up roughly 1/10 of this, so that is then only 5%. On the other hand, if you make several mistakes in a non-systematic way, these will balance out against each other, and so you will have a positive and negative mistakes. And as long as you do not make a systematic mistake, that data will be quite precise. Where you often make a really systematic mistake, where you can be wrong by order of magnitudes, is really the heat transfer to the environment by, for instance, by air cooling. As I mentioned, that heat transfer coefficient can be between 1 and 10 watt per square meter in Kelvin, and so that value can really have a big effect, and that means it is always important also to make fluidal computations in order to get precise values. Okay, so the thermal resistance of a single layer, we have already seen it. It's the thickness divided by the area and divided by by the thermal conductivity, and in that way we can assemble the thermal resistance either in a linear way, or we can do it in a similar way for parallel resistors. And what also is important, that when we have layers, for instance, if we have a small layer and a large layer, what is the proper area? The heat comes in here. Let's assume the heat that comes is in a uniform way. In high power systems, it will only come out here. In systems which have low power and a good heat distribution, it will come out in a uniform way. But in fact, that's not really the case, but in fact, the heat will come out maybe in that way. So not here in the middle, not uniform over the second cross section. And to that purpose, so-called spreading factors can be introduced, but I will not go into the details. If you are interested, you can look for the Kennedy diagram, and then it can be estimated. In our exam, we just take an estimate of how the area would be, and we assume that we have ideal spreading of the heat, which is not really the true case, but it's the first estimate. Okay, now let's come to heat transfer with radiation. If we have an area alpha A, and that area has a temperature on the heat source of that area, the dissipated power is proportional to the area. It's proportional to an emission coefficient and proportional to a constant, which is a Stefan Boltzmann constant. On the other hand, if we have a body, that body is hotter than the environment, so it radiates against the environment, but also the environment always radiates against that body. So that brings back energy. And in that way, the power is the difference between the powers which the body radiates away and the power which it receives by radiation from the environment. In the case when we have a black body which has an emission coefficient of 1, then we can say the thermal resistance of a certain area is, and the environment is cold. Then we can say it's 1 divided by 4 times the Stefan Boltzmann constant times the area times the temperature to the power of 3, so, and the inverse, of course, of it. And in that way, also a radiating body has a thermal resistance. Unfortunately, we have a problem now. This emission coefficient, which is also the absorption coefficient of radiation, is somewhere between 0 and 1. And that depends on the type of material, and that value is often not well defined, and also many radiating surfaces are not uniform, but they have some pattern on it, and so this epsilon can be variable. Just to give you some estimates, if we have a noble metal, gold, silver, copper, polished, the emission coefficient is only 2%, 0.02. Aluminum is also low when it's polished, but it always has a very small layer of oxide, and that already increases the emission coefficient by a factor of 2. So you could say when the emission coefficient is low, you will also make a large relative mistake in the power you estimate. If aluminum is black anodized, like for instance many heat sinks are of black anodized aluminum, then it has a coefficient of roughly 0.86 or something the like. Just black paint, varnish, can be in a similar range. Glass, which is smooth, also absorbs and also emits lots of energy, or a large portion of the energy. So in that way, we can never be sure what is the emission coefficient. And so in that way, in radiation, it's not easy to estimate the dissipated power. On the other hand, why do we have a problem? We must say at temperatures up to almost 200 degrees centigrade, radiation of heat is not really important for the cooling of the device. I supervised a master thesis, and here it was the estimation of the temperature in a satellite. And in that case, emission coefficients are of utmost importance, because there is no other mechanism which takes away heat of a satellite which floats in space and which is in vacuum, which doesn't transfer any heat. Yeah. So in that case, cooling is important even at lower temperatures than 200 degrees centigrade. On ground, on the Earth, it's not so. Some start looking at emission from 150 degrees centigrade on. Then why is it important? And now let's have a look at the thermal image. For instance, that is a small power device we had in an infrared camera. And you can see the camera is turned off. We have just a very small radiation. So maybe there is a very small power dissipation in that device which is in idle mode. On the other hand, it also could be that big differences in the emission coefficient could affect the indicated temperature here. So that means that is cold. Here we can also see we assume an emission coefficient of 0.78. Now we turn it on, and here we can see based on that emission coefficient we see a temperature of 167 degrees centigrade. The question is that temperature true? And we can say no, it's not true if we didn't calibrate for that emission coefficient. So for instance, you must make, at least at one point, an independent measurement, and you must calibrate the surface on which you want to make temperature. And that's the reason why emission of infrared radiation is very important in electronics, not for cooling, but for contact-free measurement of temperature distributions in assemblies. Now let's go to other cooling mechanisms, and one very efficient mechanism is convective cooling. And now imagine we have 1 square meter of area, and depending on the temperature difference, we will have a heat flux. And if it's a linear behavior, so if it's in some way a thermal resistance, then we can say we have a proportional behavior between surface heat flux and temperature difference on such a surface. And now for using air for cooling, natural convection plus radiation, we can say, okay, here we have proportionality, and in some way it is proportional for temperature differences from several Kelvin up to at least several hundred Kelvin. If we take forced air, it is very similar, but it's on a much higher level. So we have a linear behavior. For instance, we have a temperature difference of 10 Kelvin for a surface heat flux of 4 watt per square meter. Okay, and the next thing which we can do is we can use some cooling medium. And in former times, for instance, some supercomputers were just placed in some kind of bathtub. So the computer was in a bath or in a barrel containing fluorocarbons, and that fluorocarbon is flame retardant, non-burning, non-toxic, and so on, and that material can cool the electronics just by being in that bath. So again, it's a linear behavior, and it's even better than the forced air convection, because that natural convection of the fluorocarbon has a higher specific heat capacitance per volume or per kilogram of that material. Then we take forced water. Nobody uses natural convection in water, so we have a cooling device of water, and here we are an order of magnitude higher in that cooling. And so water cooling is very efficient, but on the other hand, we can also have some boiling cooling. That is, for instance, in a heat pipe. In a heat pipe, some materials, some medium is evaporated. As a vapor, it is transported over a large area, and it is condensed on a heat sink, and then this medium is transported back by some capillary forces. You do not need a pump, just some wicking effect leads to the drawing back this medium in a liquid form to the point where it is hot, and then it recirculates. So it's like the water in the Earth's atmosphere. It evaporates, it condensates, it flows to the point where again it starts to evaporate, and so on, and that can be done in a heat pipe. And in that way, heat pipes are of very high efficiency just to distribute heat. So heat pipe is ideal for heat distribution. While on the other hand, solid state heat conduction is not so good for distribution over large areas. And in that way, for instance, we can build devices which are often used, for instance, in laptop computers. There is one disadvantage. If the boiling is very strong, then the temperature is limited, of course, to the reference temperature is limited to the boiling point, and that also gives a limit here. Especially if some gas bubble is formed, that gas bubble will prevent the reflow of liquid material to the hot spot, and in that way the device can overheat, and at a certain surface heat flux we have a breakdown of that mechanism. So breakdown of the thermal management, and that means we have a maximum heat flux, and maybe we have a relatively small temperature difference which we can have, which is only here in that example only 20 Kelvin, and that means we are limiting the system with respect to the maximum temperatures we can have. So too high power dissipation, heat conduction will break down, the system will be destroyed. Okay, again, to give you some examples, for instance, here that was from some other source, air free convection, here they give 3 to 12 watt per square meter Kelvin. Somewhere in the middle is always a typical value. 10 to 100 we have also seen is a typical forced air with a fan. Water can be in a good system between 3,000 and 10,000. In a bad system, it can start from 600 to and so on. A bad system means just we have just a linear pipe through which we send water. There is one more thing which is important, which we also should keep in mind when we have a chip, and that chip is mounted on a substrate, and that substrate is mounted on a heatsink, and that heatsink is never flat. And so one of the methods we do is just we press it with a certain force. For instance, here we have some kind of bolts. So force. Unfortunately, both parts are never flat, and we have only local contact. So the heat has to be transported via these local contacts. So and so on. Okay, heat goes down. And now what we can do is we use a thermal grease. Normally it's white, so I make it in blue here. So we have a thermal grease. The thermal conductivity of that thermal grease is not good, but it's better than air. And so in that way also a small amount or increased amount of heat is also dissipated via the thermal grease. That is why we use thermal grease, to fill up the gaps which cannot be avoided because the surfaces are not perfectly flat. What we do not want is something like a thermal grease which is something like that, that thermal grease would not be good, because a thick layer of thermal grease will increase the thermal resistance, and in that way we must use only a small amount of that additional material. What is better? Have a flatter surface. So again, like in convection, we can see the power which is dissipated is proportional to the area, proportional to the delta T, and proportional to the heat transfer coefficient, which is again taken as a linear data. That heat transfer coefficient is still harder to determine than it is the heat transfer coefficient for convection. So typically on just solid state surfaces, it can vary in a range of 2,000 to 100,000. So if in the exam you take something like 20,000 to 50,000, it would be okay for me. Yeah, I would say that. So generally, that value is the higher, the lower. No, the higher the pressure is, the smoother the surfaces are, and the softer the surfaces are. For instance, some people bring in a very thin layer of indium. So the indium is soft, and so both parts can come in better contact than they would do for hardened steel parts, for instance. Okay. Now in the next lecture we will see, based on the temperature distributions, how we can estimate stress. But for today we are finished. Thank you for your attention.